Hello, welcome back to your physics teacher. Today we're looking at projectile motion questions, and in particular is from the Nelson textbook. But today's question is actually really difficult. So that's why I want you to take your time with it and pay attention carefully. And please ask me any questions in the comments if you want me to clarify any particular point. So this is a very challenging question, and I encourage you to just ask me questions if you have any along the way. So let's start question number 6. An acrobat is launched from a cannon at an angle of 60 degrees above the horizontal. The acrobat is caught by a safety net mounted horizontally at the height from which he was initially launched. Suppose the acrobat is launched at a speed of 26 meters per second. How long does it take before he reaches his maximum height? And how long does it take in total for him to reach a point halfway back down to the ground? Okay, that was a lot. So we have an acrobat, there's a cannon, maybe like at the circus, and they're getting launched at an angle. This angle is 60 degrees to the horizontal. So whenever they say the horizontal, they mean the x-axis. 60 degrees from the horizontal. Now, the interesting part about this question is that they're telling you that the acrobat lands at the same height from which he was launched. So what does that mean about the vertical displacement? And the total vertical displacement, it will be 0. So that's an interesting idea to consider here. Now, for any question that we want to solve, the best thing to always do first is to visualize it. So we just kind of talked about it. But now let's draw a picture so we could visualize it even better. So here we have a person on a cannon. Maybe I should lower it a bit. Okay. And the trajectory of any projectile in the air is always going to be Newton's rainbow, which means a parabola that opens downwards. The interesting part in this question, they told us that the acrobat lands at the same height from which he was launched. So maybe there's a safety net here. Now, what are some of the things that were given? They're giving us that the initial launching angle is at 60 degrees above the horizontal. So the horizontal is just the x-axis. So we want to set up the coordinate system, and then now we have our initial launching velocity at 60 degrees to the x-axis. So we could label this angle. Normally we call the launching angle theta. Theta is 60 degrees, and the initial launching angle, we call it V initial. And the initial speed, it was 26 meters per second. So once you visualize it, you draw your coordinate system, you drew what you were given, then you want to start to label your other vector quantities like displacement, velocity, acceleration, and time intervals. But our displacement, here we have a different points along the journey, because they're asking us how long does it take before he reaches his maximum height. So the first displacement that we're interested in is the vertical displacement to reach the maximum height. So let's call this delta d y top. So at the top, at the maximum height. And this would be the horizontal displacement that it took to reach the top height. So let's call it delta dx top. So once you have your displacement, then remember that whenever you have any projectile, it's always going to experience the acceleration due to gravity, which is pointing downwards throughout the entire motion. So A equals to G, which we approximated to be negative 9.8 meters per second squared. And the time that we're interested to find is the time that it takes to reach the maximum height. So let's call this delta T top, which is our unknown. So once you've drawn this picture, now what we can do, we can make it smaller so that way we have some space to write down our equations. You can't make it small, but I can. I'm using the iPad, which I recommend. Maybe you want to pick one up. Not that I'm supporting Apple or anything, but I like Apple products. Okay, so they want to find out how long it takes to reach the maximum height. Now, what's really interesting about projectile is whenever an object reaches the maximum height, it is always going to be momentarily at rest. But because we're dealing with projectile, we have to differentiate the y component from the x component. So as we know that the acceleration is only pointing down, this means that the velocity is only changing along the y component, and the x component stays constant. Now, to make it clear, refer to my diagram. So at the very top, the velocity is not zero because it has still some horizontal components. So v top, maybe vx top would be better. Vx top. So the velocity at the top is not zero horizontally, but vertically the velocity at the top is zero because it's momentarily at rest. So remember, we talked about this before. So vy top equals to 0. Now if you want a better explanation, so I'm going to draw another velocity vector. Just as it's going up, because vertically it's slowing down, horizontally it doesn't change. And as you go even higher, vertically the component gets smaller, but horizontally it doesn't change. Right, so here horizontally it's staying the same length, but vertically it gets smaller until it reaches the top. Then vertically the velocity is going to be 0. Now that's the key part for most projectile questions. The vertical component is 0 at the maximum height. Please ask me questions if you have any. Please subscribe as well if you're watching and you're a new viewer. Now the part that we're going to do next is to find the time that it takes to reach the top. We're going to use our kinematic equations of motion, and because now we have the extra piece of information that the velocity is 0 vertically at the top. So let's use our equations of motion. The one I always tell you to start off with, the main equation, this is number 1. Now normally this is always my main go-to equation, but in this case we can't use it because we don't know the time interval and we don't know the displacement. So that's not a good idea. But keep in mind that we do have other equations that we can use. So in this case, when this happens, when I have two unknowns in one equation, I move on. So I'm going to use my other equations. So equation number 2 that I usually call it. Now if you look at this equation, it depends on the final velocity, which vertically at the top is 0. The initial velocity, we can find out acceleration due to gravity, and the time interval is what we're looking for. So this is the equation that we're going to be using. But because these are all vectors, we have to remember we have to use them along the x and along the y component. So let's break this down. So along the y component, because that's what we're interested in at the moment, v final y equals to v initial y plus g delta t, where I'm just using the fact that the acceleration due to gravity is vertically, so I replace the acceleration by the letter g. And at the very top, which is my final in this case, we said vertically is 0, so we can make that substitution. V initial y plus g delta t. Now my target is to find the delta t, but I need to first go back and find my component of the vertical velocity. So what does this mean? I have to go back to my velocity vector, and because I was given the angle, I need to break it down along the x and along the y component. So normally I should have done this before, but sometimes I forget this step, so I have to go back and do it. So what am I referring to? Because our initial velocity vector, if I was to redraw it, it has a magnitude of 26 meters per second. And the angle, which is made relative to the horizontal, is 60 degrees. So I can find the components. So the components are just the v initial x and v initial y. So here this is a right angle triangle, Yusoka-Toa. So if you remember, I showed you a previous trick. If the angle is always given closest to the x-axis, then the horizontal component is always cosine, and the vertical component is always sine of the angle. So I'm skipping a step, but again, refer back to my previous videos and section 2.2. So again, horizontal, if you're given the angle closest to the x-axis, is going to be the cosine ratio, and vertically the sine ratio. Now why that's helpful is because now I can just substitute in my y component of velocity initially into the equation below. And if we look at this, vertically the velocity component points up, and horizontally it points to the right. So if you recall, whenever a vector points up, we're going to take it as positive, and whenever the vector points down, we're going to take it as negative. So this would be 26 sine 60 minus g delta t. We could call it delta t top, right? Because that was the time to reach the top. Let's do some algebra. Oh, this is taking quite long. I was hoping to finish only in 15 minutes, so stay with me. As I was mentioning, this is not even the hard part of the question. The hard part is still coming up. So to isolate for delta t, divide both sides by negative g. So I have negative 26 sine 60 divided by negative g, which was 9.8. So let's put it into the calculator. We get approximately 2.3 seconds. That seems reasonable. So the time the acrobat takes to reach the maximum height is 2.3 seconds. And I think that's what the question was asking us for part A, right? How long does it take to reach the maximum height? Yeah, 2.3 seconds. Now the hard part. How long does it take in total for him to reach a point halfway back down to the ground? So how long does it take for him in total for him to reach a point halfway back down to the ground? So let's draw the trajectory again. Trajectory is just a fancy word of saying the path traveled. So we know Newton's rainbow is a parabola that opens down, which is the path of the object. And the time that it took to reach the maximum height was, what was it, 2.3 seconds. But what we're interested in is to find the time in total it takes for him to reach back a point halfway back down. So let me just label this in the diagram. So we're looking for the time to reach this point. So this means that if my maximum height is given by delta dy top, then the halfway point of that will be divided by 2, right? Halfway. Delta dy top divided by 2. The halfway. Now, this is where it could get tricky, because you might be tempted to think, because it takes 2.3 seconds to reach the top, then it takes another 2.3 seconds to reach back down. And that is correct. So what does that mean? In total, the time that it will take to hit back the ground, not the ground, but the safety net, will be 2.3 times 2. But now they're asking us for the halfway point back down to the ground. So you might be tempted to think, well, because it takes another 2.3 seconds to hit the ground, then maybe half the time it'll take to reach halfway back down to halfway to the maximum height. Wow, I hope you can follow that. That is quite tough. Or you could just rewind that part. But because a parabola, that's not going to be true. Because if you think about it, whenever an object is falling vertically, it is speeding up. So it is not covering the same distance in every second of time that goes by. So first it covers less distance, then it covers more distance. So it's speeding up. So the time will not just be halfway the time that it takes to fall back down. So this is not the half of the total time. Okay, I justified it as much as I could by reasoning. Now I'm going to show it to you through calculations, which is what makes this question difficult, because it's very tempting to just say, oh, well, half of 2.3 and I add on to that and then that's it. And you think you're clever, but you will have gotten it wrong. So what we're going to do to find out the total time that it takes to reach halfway back down to the ground is going to be, first we want to figure out what is the maximum height, Once we know how much is the maximum height, we want to figure out the time that it takes to reach halfway the maximum height. So the first thing that we want to do, find the maximum height. But what are we given? We have initial velocity along the y, we have the final velocity along the y, we have acceleration. We're looking for displacement. Actually, in this case, there's two ways you can solve it. There's two equations that you can use. So you can use v final square minus v initial square equals to 2a delta d. You can use that equation. Or you can use delta d equals to v initial plus v final divided by 2 times the change in time. So both of these equations will give you the right answer. My preference is to use the one on the left, but you could use the one on the right. So maybe I leave it up to you to try that out. So using the equation on the left, let's solve for the y component, and we're looking for maximum height. So vertically at the maximum height, we said the final velocity is going to be 0. And our initial velocity is going to be the y component. Our acceleration is due to gravity, so negative g. And our vertical displacement will be pointing up, so that will be delta dy top. Now isolating, we get left with delta dy top equals to negative v initial y squared divided by negative 2g. Notice the negatives will cancel out. So this gives you v initial y squared divided by 2g. But if you recall, we already have the vertical velocity initially, right? We broke down the velocity vector. And vertically, it was 26 sine 60. Okay, let's calculate this. We got approximately the maximum height. It was 25.87 meters. And again, this was one way, using one equation. You could have used the other equation and verify that you get the same result. But the question asking us how long it takes to reach the point halfway back down to the ground. So now that we know the maximum height, we want to look for the maximum height divided by 2. So divide by 2. This will be a value of about 13 meters. So now that we have a vertical displacement to be 13 meters, we want to find out the time at which the object was at 13 meters height. So again, because we have the trajectory equation, which is the main equation that we always start with, equation 1, now we want to find out the time at which it's at the 13 meter mark. So if you notice, it's at 13 meters at 2 points. Right before we reach the maximum height and after the maximum height. So there's going to be 2 solutions. It kind of gives you a hint. When are you going to get 2 solutions? Whenever we have delta t squared, which is the main equation. So let's put it into the main equation to find the time. I told you this question is hard. But I guess that's why you're here, right? For homework help. If it was easy, you wouldn't have been watching the video. So make sure you hit a like and show some support, okay? So time when object is 13 meters high. And now I'm using the vertical component, and let's make some substitutions. This would be 13 meters. V initial y, we done this already. It was the 26 sine 60 delta t. G points down, so we put a negative. I'm bringing the 13 to the other side of the equation. Now I'm trying to do a little bit something clever. I purposely made the delta t a different color. And I did this so it can remind you that that's your unknown. But even more than that, that our unknown is quadratic with time. In other words, that we're going to have to think about this as a quadratic equation. So this means that we have c plus bx plus ax squared. So this unknown is actually quadratic in time, and to solve for it, we have to use the quadratic formula. But to do that, first we have to match the coefficients of the general formula with what we have in our specific case. So by comparing the two general forms, a is actually negative a half of g, b is 26 sine 60, and c is negative 13. And again, this is from the quadratic equation. I compared it to quadratic in time. Now to solve for it, we try to relate the c, b, and a values because we're going to be using the quadratic formula. There's a rhyme for the quadratic formula, remember? So we have delta x equals to minus b plus or minus square root of b squared minus 4ac divided by 2a. Hopefully your formula sheet has this because it's not an easy formula to remember. Now here comes the monster trying to put this all into this formula. It's really intense. Likely you're going to make a mistake because it's very hard to not make a mistake in this part. If I made a mistake, please let me know in the video. That'd be embarrassing, but let me know. Things are so intense. I had to go quiet because it's very easy to make a mistake, so I'm nervous. Hopefully I don't. Okay, so let me put it into the calculator and you could check with me too. Hopefully we do it correctly. X, which is our delta t, I got two solutions, which is what we expected. The first solution is 0.7 seconds. The second solution is 3.9 seconds. which makes sense because I said that the object's trajectory, it's at 13 meters at two different points, before the halfway point and after the halfway point. So we expected a number to be more than 2.3, which is 3.9 seconds, but it should have been a number less than 4.6 because 4.6 would have been the total time, right? So see how you can reason that out, that it makes sense? So now I think I'm correct, so don't try to correct me and say, oh, Mr. Morales, you're wrong. So I'm very confident that I'm correct. That's it, that's this question. Very intense. Go through it on your own, try to do it on your own, and there's more than one way of solving it. This is just one way. Please feel free to use your own style, and stay tuned. I'm going to show you more difficult questions. So I'll see you in the next one. Bye-bye.